Hey guys, okay, so today we're going to talk about plate tectonics and the theory of continental drift. And how the Earth's crust is in motion. So there are a couple of early tectonic theories that we can talk about with plate tectonics, which is the most current theory. The first theory, early theory of how plates were moving was a contraction of Earth due to cooling. So in this theory, as the Earth cooled, it contracted, causing sea levels to rise and cover old land bridges. This theory was used to explain how mountain formation and folding occurred. Then they had the theory that expansion was due to heating. So after science discovered radioactivity, they said that as Earth expanded, the continents split apart and valleys and rifts formed. So these two theories didn't really answer how exactly the plates moved apart, or how we got a lot of the geologic features we see on Earth. Then we come up with the theory of continental drift. So in 1910, Alfred Wegener began to wonder, what's the relationship between the continents? So perhaps all of them used to be connected. And the theory of continental drift says that there's a slow movement of continents over Earth's surface. It was thought to be caused by the rotation of Earth and the tides over 300 million years ago. So if we look at what Earth looked like 300 million years ago, we see that it has a supercontinent known as Pangaea. And Pangaea means all land. In this Pangaea, the reptiles and insects were very similar. There were tropical forests, coal deposits within all of these areas. So if we look here at this reconstruction, we can see first at 0 million years we have Pangaea, and we have all these coal deposits and tropical forests form. And over time, you can watch the red lines move as they separate to what we now see as current day Earth. So Wegener looked for much evidence throughout the entire world for continental drift, and he came up with three main points of evidence for continental drift. The first one was fossil clues. Fossils did support continental drift. Fossils of plants and animals were located in both South America and Africa. The same type of fossil, for instance, type of alligator, might have been found both in South America and in Africa. Well, we know that the alligator couldn't swim there, so how did the fossil of that animal get to both places? And here on this map, you can see the different types of animals and where they were found all over the different parts of the world. So they must have been connected at some point. Another piece of evidence Wegener had was fossil clues. So the fossils of warm weather plants, now these are fossils, were found on islands in the Arctic Ocean. So if they're warm weather plant fossils, they can't survive in the Arctic. So how did they get there? Well, that area must have been warm at one point. In addition, glacial deposits and rock surfaces were found in South America, Africa, and India, and Australia. His last piece of evidence was rock clues. The rocks that make up the continents where they were joined, such as here between South America and Africa, or between Antarctica and Africa, were very similar in age and in composition. Now, Wegener's theory was not widely accepted. In fact, it was actually widely rejected. The reason for that is that he couldn't explain how the continents moved. He thought the continents simply plowed through the crust, which now today we realize is not true. There's further evidence for plate motion. This was seafloor spreading. So Wegener died, and his theory kind of was buried with him for a little while. It continued to move on. People continued to look for evidence, but it wasn't until the 1940s, I guess, after World War II, that they realized that the seafloor was actually spreading. So prior to the 19th century, most thought the ocean was flat. And in the 1850s, the first bathymetry map of the ocean floor was created. This showed vast underwater mountain ranges. Further exploration due to sonar showed even more underwater topography. There's very little sediment buildup on the ocean floor. What we couldn't figure out is why there was so little sediment. If the Earth was 4.6 billion years old, then there should be a lot more sediment on the ocean floor than is there currently. So relatively young fossils are on the ocean floor compared to the age of Earth. So based upon the presence of underwater mountain ranges, mid-ocean ridges, and fossil evidence, the theory of seafloor spreading was developed by Harry Hess in the 1960s. Harry Hess said the ocean floor rock was only a few 100 million years old, while the Earth was much older. New ocean floor is created as large slabs of Earth, called plates, pull apart. That magma rises up and pushes old rock outward. This further explained how the Earth crust moves. Now, there's two pieces of evidence that Hess had for seafloor spreading. So, first one was rock samples. They found that the crust is very thin in places of oceanic crust. And they found that the youngest rocks are located at the mid-ocean ridge, and the oldest rocks were furthest from the ridge. When they took these samples, they found that no fossil was older than 180 million years old, which leads us to believe that none of the ocean crust is older than 180 million years old. The other piece of evidence was magnetic clues. So as magma comes to the surface, magnetic minerals such as magnetite align with the magnetic North Pole. And if you look at these magnetic minerals, they can actually see that they reverse over millions of years. Just like if you take two magnets and you put them together and sometimes they'll attract or repel, you can look at the magnetic minerals to see which way they will attract and repel to see the magnetic clues. So if the seafloor is spreading, why isn't the Earth becoming bigger? Well, the reason for that is that the new crust is continually being created at the mid-ocean ridges, but it was also subducting in different areas, which are what we call trenches. So in addition to this, we also have to be aware of the interior structure of the Earth. If Wegener had been aware of the internal structure of the Earth, he may have been able to better explain why plates moved. So there are two ways of thinking about the Earth's layers. The first is the compositional layers, and the second is the physical layers. The first is the familiar layers. These are based on composition. And there are three main layers in composition. There's the crust, the mantle, and the core. The crust is the thinnest layer. It's only about 5 to 100 kilometers thick in most places, and it contains the greatest amount of silica. It's split into two types, oceanic and continental crust. The mantle is the thickest layer, and it contains a lot more iron and magnesium and calcium than the crust. It contains some silicates, but much less than the crust. No one has ever drilled into the mantle because it is so hot it would melt any drilling equipment. So we've never been able to get into the mantle. In fact, we haven't even been able to get through most of the crust. Now the most inner layer is the inner core. This is made up of solid iron and nickel. It's extremely dense and radioactive. The other way we can think about the Earth is its physical layers. So in here we have, again, we talk about spheres as far as lithosphere, hydrosphere, anthosphere. Well, here we also have the spheres of Earth. We have the lithosphere, which is the rock sphere, the tectonic plates, the combination of crust in the upper region of the mantle. It's cold and brittle, cold being relative compared to the other pieces, the inner layers, and it's easily broken. That's why we have the plates, because they easily break. Then we have the asthenosphere. The asthenosphere is the part of the mantle that is almost like a warm tar or honey, if we had to give it a consistency. It's kind of what the lithosphere floats on. Then you have the mesosphere. It's much stronger than the asthenosphere. It's the middle layer. Then you have the outer core, which is liquid, and then you have the inner core, which is solid. So these are the different layers of Earth, and we're going to now get into, with our next lesson, what the theory of plate tectonics is, because we've taken the history of how the Earth, early tectonic theories, then we go into continental drift and seafloor spreading. We're going to pull all that together in the next lesson, which will be about the theory of plate tectonics. So what you guys are going to do now is fill out your WSQ on continental drift theory, and I will see you in class tomorrow.